Let's follow a more classical approach. When you throw a ball at a hill, it will stop at certain height and it will come down. This is because the ball don't have enough kinetic energy to overcome the hill's potential energy, and that's why it comes down. But in quantum mechanics, things aren't so simple. Let's just replace the ball with the electron and the hill with a potential barrier. Sometimes the electron, even if it doesn't have enough kinetic energy, can jump on the other side. Boom! But how does this happen? One thing is really important to understand, that we can't pinpoint electron at one location. It can be here, it can be here, it can be here, or all the places at the same time. Well, this comes from Heisenberg uncertainty principle, which says that you can know the speed and the location of a quantum particle at the same time. But no worries, we have our wave function friend. Wave function allows us to find the probability of where electron can be. Like here you have 70% probability, then you have just 10%. A wave function is denoted by Greek letter psi. Now instead of picturing the electron as particle, picture it as more like wave. But wait, waves reflect. So what's on the other side? Well, there's a secret property of wave you must have never ever learned at the school. Light is an electromagnetic wave. So let's see what will happen if you throw it from a piece of glass. Obviously, it will refract. Refraction is when light bends at a particular angle. But it isn't the only thing it does. It also reflects. The light being reflected or refracted depends upon the angle. All beams have a particular angle where 100% of incoming light is reflected, and this is called as the total internal reflection. But that's not true. These are the Maxwell equations, and they may look innocent to you, but they form the whole foundation of classical electromagnetism. Remember how we said light was an electromagnetic wave? When we solve these equations with the total internal reflection, we get something very interesting. Isn't it very interesting? Physicists called it the evanescent wave. Well, I personally think that this is a perfect name, because evanescent means quickly running out of existence or fading away. The evanescent wave lasts only a few wavelengths and vanishes. And that's why we can't detect it. But if we place a material close to evanescent wave, it doesn't decay completely and continue to travel further. This thing is called the frustrated total internal reflection, and the small wave is the reason of the whole quantum tunneling. Okay, back to our potential barrier diagram. We saw that the waves actually reflected, but some of the wave actually made it through. And that is nothing but our evanescent wave. This allows very, very few but non-zero amounts of electrons here. So many of them are being reflected here and very few of them make it through. So this was the quantum tunneling. But scientists are still confused that is the wave function a real wave or just a mathematical model? But what they do know that it perfectly explains the whole quantum tunneling thing and how electron passes from here to here. So that was all for today's video. Thank you so much for viewing it.